let's take a step back and look at left and right inverses. You have your matrix is a square matrix and it's got full rank. Then you can invert it. It's an invertible matrix. It's not a singular matrix. And there is an inverse, and that inverse can be multiplied on the left or on the right. What I mean is this. If it is a full rank matrix, then the inverse exists. That is A inverse. A inverse times A or A times A inverse will both be equal to identity matrix. So A inverse is a real double-sided inverse. So that's what we have. But if it is a full column rank matrix, it's not a square matrix, so it doesn't have an inverse. But if it is a full column rank matrix, then we know that all columns are linearly independent. The rank is n because n linearly independent columns, and it's got more rows than columns. And if you consider A transpose A, that matrix is going to be a smaller matrix because n is much smaller, and A transpose A will have the size n by n. But A transpose A is a full rank matrix because it's got a rank n and its size is n by n. So it's a full rank matrix. So A transpose A has an inverse. So I can write A transpose A inverse times A transpose A is equal to I. And after that, if I look at it and I say that this much multiplying A on the left is giving me I, so whatever I have there on the left, that is the left inverse. So that is how you would kind of derive left inverse whenever you need it. And if you have full row rank, which is like the transpose case of a full column rank, then it has a right inverse. All the rows are linearly independent, and the rank is a number of linearly independent rows, which is m. A transpose is going to have size m by m, and then you can do this. You can say A transpose times A transpose inverse is equal to I. So this much, the green part, that becomes the right inverse. So that is just a recap of left and right inverse and real full inverse also. Now this is for matrices that are full rank, square matrix, full column rank, or full row rank. What happens if it is a general matrix which doesn't have full column rank or full row rank? It is just a matrix. So what you do there? What you do there is the pseudo-inverse. And so the pseudo-inverse will kind of reduce to a normal inverse if it is a full rank square matrix, will reduce to a left inverse if it is a full column rank, and if it is full row rank, it will reduce to the right inverse. So there is a pseudo-inverse, and that also you get from SVD. So that definition of pseudo-inverse is when it is rank deficient and it is not square either. So here we cannot really get anything like an identity matrix, so we're going to manage our expectations. So we're going to define a pseudo-inverse A plus. That is a definition. We're not looking for A times A plus equal to I, that we cannot have. So we will say something more modest like A times A plus A, that is equal to A. So A, something multiplying A gives you A. So this is like the identity matrix, but it's not quite the identity matrix. Similarly, I have another one, A plus A times A plus, and that has that gives me A plus also. So that's another requirement. That is another requirement. And then we require that A plus A and A plus, they should be symmetric. Okay, so these guys are symmetric. After having these requirements, after finding some A plus that satisfies these requirements, then we can go back and look at our favorite equation, AX equal to B. Now what we know is that for a B that is non-zero, the X will be in the row space. That we know if you solve it, and we have some X and some B, and if B is non-zero, then we know that X is going to be in the row space. So it's a mapping from the row space to the column space. Now if you multiply this guy with A plus, you know that A plus A is equal to just A. That is our first requirement here. So we will get AX is equal to this guy. What it means is that A plus B is equal to B, because what do we have? I have AX is equal to this guy, and AX is also equal to B. So AX equal to B, that is what we started from. But what we have from the other side is that A times A plus B is equal to the same thing. But let's see what it is actually saying. So what it is saying is that A plus B takes the place of X. So for a non-zero B, A plus B is in the row space of A. So A plus is actually a mapping from the column space. Remember, B is in the column space and A plus B is in the row space. So it's a mapping. It takes B in the column space and gives you something in the row space. So what it is doing is actually inverting the transformation AX equal to B, but specifically within the row space and the column space. Everything in the row space goes to the column space in a 1-to-1 onto fashion. So it can be inverted within that confines. So A plus is the guy that actually does it. A plus takes vectors in the column space, gives you vectors, a unique vector for each one of the unique vectors in the column space, gives you a unique vector in the row space. Okay, so it is like the inverse, but confined to the column space and row space, where you can actually do the inverse. This is the best you can do. You cannot do better than this. So let me summarize that in that box there. A plus is a mapping from Rm, which is the codomain, the output space, to Rn, which is the domain, the input space, such that A plus B is actually X for every B that is a member of the column space of A. So the pseudo-inverse actually does the best we could possibly do with a very general matrix which doesn't have full rank, etc. This is the best you can do. And computation of this guy actually comes from SVD. So we can actually do this computation. We have SVD right there. And if you take the pseudo-inverse, we will get you remember when you take the inverse, it actually goes in the opposite direction. So you're going to take the inverse of U, that becomes U transpose, inverse of V transpose, that becomes V, and then we're going to take the sigma matrix and we're going to take the reciprocals wherever we have a number, and if it is 0, we're just going to leave it as 0. So that's the definition of the pseudo-inverse. This is using the full SVD, and we can actually do the same thing using the economic version of SVD, the smaller version of SVD, which is actually a bit easier to understand. The most important part is that it's a mapping from the output space back to the input space. So that kind of completes the symmetry that you have among the 4 fundamental subspaces of the matrix. So let me show that to you. So we started quite a while ago with general matrices of m rows and n columns, R m by n, with the rank R, which may be smaller than m and n. So that is the general case, and that is actually a mapping from Rn to Rn. Rn is the domain where the vectors of the kind x live, and Rm is the codomain or the output space where vectors of the kind b will live. So it's a mapping from Rn to Rn. And we have the row space and the column space. Every single vector in the row space will go to a unique vector in the column space through the application Ax equal to b. It's a linear combination of the columns of A, and all such linear combinations are in the column space. And by doing SVD, we could find special basis in the row space, an orthonormal basis, which will transform to a special basis in the column space, an orthonormal basis there. Of course, if you have a 0 vector, which will be a part of the row space and column space and all spaces, that will of course go to the 0 vector, because A times 0 is always 0. Or what is a bit more interesting is that everything in the null space will also go to the 0 vector on the output side. 0 vector is a part of the column space also. There is a left null space, so we've accounted for all the dimensions in the input side. They all go somewhere in the column space, but there are other vectors. So if the row space is the xy plane and the null space is the z-axis, there are many more vectors in R3, and those are all linear combinations of vectors in the row space and the null space. But in order to complete the story of the dimensions, in the input side, in the domain, we have R basis vectors in the row space, the right singular vectors, vi's from v1 to vr, and the rest of them are actually in the null space, and that there will be n minus r of them, because that is the dimension of the null space. Similarly, there are some u vectors that will complete the basis on the output side. And what I was just telling you is that most of the vectors that are not in the row space or the null space, those are most of the vectors in the input side. They are not in the xy plane or the z-axis, but will be somewhere else. All those guys will actually end up in the column space. The important part is that everything that is in the row space goes to the column space in the unique fashion. There is a 1-to-1 mapping, so that can be inverted, and that inversion is done by A plus, which is the pseudo-inverse. So that will take all the vectors in the column space back to the row space, and of course the 0 vector will go to the 0 vector, and everything in the null space by the action of the pseudo-inverse will go to the 0 vector too. And most vectors on the output side are neither in the column space nor in the left null space, and they will end up in the row space by the action of A plus, the pseudo-inverse. So that completes the symmetry. If you look at this picture, to me, this is the most beautiful picture that I've shown you in the textbook in this course. This is completely symmetric. This is the summary of almost everything that we did in this course. Today,